Hi, Kevin. How's it going?
It's going well.
I'm still getting organized here.
Yeah, I'm trying to get a grip on what we were doing last time.
Yeah, me too. Do you see the last thing we looked at?
So let's see here. Using the creation annihilation operators acting on a vacuum state to produce the in states, which will have nothing in common with the out states. We were approaching a trick we were going to be using.
Okay, yeah.
Yeah, there's some trick notes.
Yeah, so I probably wrote the creation and annihilation operators with that double arrow notation. Do you see that there?
I remember it.
Yeah.
Oh, there it is. Yep. And that just, I mean, why do we use that as opposed to like maybe like the Lie derivative notation or something? Is it the same thing?
The Lie derivative? Is that a Lie derivative? Oh, I guess the Lie derivative is a sort of commutator, isn't it? Hey, Eli. I'm not sure that is a Lie derivative. It's just a combination. You know, it could be. I don't actually know. That's an interesting question. It's just a simpler way of writing this difference between two terms that comes up. So yeah, because the momentum conjugate to phi is just a time derivative, and the frequency is a time derivative of a plane wave, you can write it that way. But as far as I know, it's just a shorthand trick like the slash on vectors to denote a contraction with gamma. It's just some a quicker way to write some stuff that people developed.
Yeah, make our equations look easier than they are.
Yeah, that's right.
I say that with a joke. But.
Yeah, you know, always possible. It has some deeper meaning.
I mean, yeah, I think if you can find an elegant way to express things concisely, then that's useful.
Yeah, it's just simpler. You know, you define things like this all the time. You know, when we're doing research calculations, you know, Eli, you're going to see plenty of this. You know, you get some long expression and you realize you're carrying a third of it around every time, repeating it and not doing anything. You give it a name, right? It's no different than that, really. And you know, if that thing crops up enough, you call it the energy or something, right? You derive some formal properties for it, and it becomes, you know, a research area in mathematics or something.
Sure.
Let's see. So how are we doing here? Oh, people are arriving. Good. Hey, Guillermo. Thanks for your talk earlier.
I'm glad you enjoyed it.
Yeah. You know, starting off with a two-particle example would have been helpful, I think. To me, you know, I mean, clearly some people were sort of familiar with this already.
I would second that piece of feedback. Yeah, everything was pretty awesome and informative, but I was just feeling a little lost out of the gate because I wasn't sure what problem we were actually solving. But then we addressed that, yeah.
Electron system. That's
no, I got it. Yeah.
It's yeah,
I got you. I mean, that makes sense.
A trick to any kind of presentation is you know, the first third of it should be something everybody already knows. You know, you want people to feel comfortable, feel like, yeah, they know what they're talking about because I understand this, right? And so, yeah, giving really familiar information that you're probably way beyond at the time you're giving the talk, but keeps people in. But anyway, yeah, thanks for your presentation. Now, let me see, who are we missing? A couple people yet. So anyway, let's continue our recap of where we were. Kevin and I were just recalling writing the raising and lowering operators using this double arrow notation, but otherwise it's the same expression where the double arrow differentiates to the right, and then you subtract the derivative of the whatever function is to the left. So now we're going back to the transition amplitude. We're going to imagine an initial state at asymptotic pass time with m particles and a final state with n particles. So the particle number, of course, can change. You know, in actual calculations, we're liable to restrict this to 2 or 3 incoming particles and 2 or 3 outgoing particles, but we can do the general formalism here. And what we're going to do is to eliminate all of the properties of those initial states. So we're looking at a transition amplitude. Let me start up here. So we've got P1 momenta through Pn coming out at some final time. And we want to know how that's related to Q1 through Qm at some initial time. And what we're going to do, okay, so these states are characterized by these momenta. And the thing we're going to do is extract some operators, basically creation and annihilation operators at first, that remove one momentum at a time from the initial state, so that what we end up with are a bunch of operators acting on the vacuum state here. And hey, Alex, welcome. Let's see, and then let's see, Tyler's still missing. All right. So how do we do that? Well, yeah, it's exactly that, right? So we've got, I'm just going to write PI here to represent the whole list of them. So it's not any particular one, it's all of them. Then we have an A dagger of Q1. How else do I want to characterize this? Do I need to? Oh, well, just at that initial time, acting on a state that now has Q2 through Qm at that initial time. And then we're going to write that as the,
Could I potentially request a change of index? Or I feel like we've got too many I's showing up playing too many roles. Because we have PI as an index, and then we also have I indicating an initial.
Initial time T0, does that help?
Yeah.
Let's see, did I use it anywhere else? And this is just, this is P1 through Pn, if that helps.
Yeah, that 0 helps, I think.
Okay, good. Yeah. Yeah, yeah, good notation goes a long way. All right, so now there are two things we're going to do here, and I have to think about which. Have to see where it is that I'm actually doing this insertion. Yeah, I think I can work with just this creation operator, but this is an in state, and I can replace that by a in dagger minus a out dagger, also at Q1, but both of these at Q1. And I can make that replacement because we're assuming that everything scatters. So if that A out is adjoint is looked at as an annihilation operator acting on the final state, it's going to give 0 because there is no Q1 in the final state. So I can add this for free because it's going to give 0 when it acts here. Now we want to put in this expression that we wrote before for A in. I'm not going to do this part right now. 2 omega z this 2 pi to the 3/2 is going to unfortunately change at some point, and we're going to take the limit as t goes off to minus infinity, and then I'm writing this A in dagger. In terms of the fields, it's a 3-dimensional integral of this double arrow acting between a plane wave e to the. Now, wait a minute. Should this be? Oh, yeah. I think I should be writing Q1 here. Dot x, and then we have D0, I believe, acting both directions, and then phi of x here. And phi is actually an operator. So this is A, where we've written it with this double arrow, and now that's acting on Q2 through Qm and that initial time. And then, back on this side, I have P1 through N at the final time, like this. So all of that gets sandwiched in between. And now, let me see if I've gotten everything here. Yeah, so, okay, so far so good. So we could similarly add an A out here, and that's a different limit. So basically adding A out gives the difference between this and a similar integral, which eventually we're gonna write as just one integral minus another, and I mean an integral sign minus another integral sign. I don't think, let's see. I don't think I need that right away for this part. I'm not sure why I introduced that here. Okay, so the trick here then is to use the Klein-Gordon field equation for this plane wave. So we've got box plus m squared on minus I Q1 dot x equals 0. Yeah, and this box is 2 time derivatives minus a Laplacian plus m squared minus I q1 dot x, and all of that is 0. So I'm going to basically unpacking this back into the D'Alembertian operator. If we look at what happens with d0 of this product, all right, so another thing we know, e to the minus I q1 dot x d0 both ways phi. Now wait, where do we get it d0 of this? Oh, right, I remember. No, I skipped a step here. Yeah, we're going to get a d0 into this because what I want to insert here is an integral over time of a derivative over time. So that's an identity operator up to some constant. But that's going to make this a full space-time integral. And it's going to give us d0 of all of this field stuff. And now we actually do get this difference because, yeah. So what we're looking at is the limit as t goes to minus infinity. Which way do I write it? Infinity. Minus the limit as t goes to minus infinity. So we're looking at that difference acting on some spatial integral of some function of x and t. And we're going to write that as the integral over time. So these limits take the limit on this time integral from minus infinity to infinity. And then we get a d dt and a d4x. So we end up with d4x of d0 of f of x and t. So that's the transformation we want. So by putting this difference, we're getting a difference between the extreme time limits so that when we insert this time derivative, we get a full space-time derivative over the full range of time of the time derivative of the thing we're looking at. Okay, so who dreamt that up, huh? You know, we're looking at a century of people mucking around trying to figure out how to do quantum field theory. And a lot of heuristics were developed, a lot of different techniques. In writing ahead of where we are in the text, I've been trying to learn the BRST quantization, brush up on it. It's the culmination of probably half a dozen different techniques for handling the gauge invariance. What we wrote down in E&M was we made some standard gauge choices, but people have tried a lot of different ways of doing that procedure that maintain the covariance. They add in something like a mass term or an explicitly gauge dependent term that breaks the symmetry while, you know, so that you actually get a conjugate momentum to all four components of the vector potential. And then, you know, after you've done everything, you restore the symmetry. Well, an even better technique is this BRST method that extends this number of fields in your Lagrangian, adds a couple of extra fields. They're actually fermionic fields. They're anti-commuting fields. it involves anti-commuting numbers. It's very much akin to supersymmetry and only was introduced after people had been studying supersymmetry for a decade or two. But it allows you to handle non-abelian gauge theories. And it's more or less the culmination of these many efforts of handling gauge. And in particular, it's best for non-abelian groups. But I would like to develop it for E&M as well. I found a good paper on it. I'll refer you guys to it. But yeah, I figured why not, do it the right way. So we're going to play with some anti-commuting numbers and things in, maybe, well, we only have a few weeks, don't we? Well, we'll I think we'll get there. Okay, now, this D0 changes this operation. I was starting to write that here, but I'm gonna run out of space if I put it there. So let's look at D0. Can you see me here? Yeah. All right, let's look at e to the minus I Q1 x D0 phi minus D0 e to the minus I Q1 dot x times phi. And there's a cross term that's going to cancel because this D0 is going to hit that and the phi. Those two terms will cancel. It's only when you get a D0 squared that you get something. So minus e to the I Q1 dot x D0 squared phi minus, okay, two time derivatives of this plane wave. We can use the wave equation to rewrite that as a Laplacian this derivative, we can use the Laplacian, and so I can replace this D0 here with Laplacian minus m squared. So this becomes e to the minus I Q1 dot x. Let me know if the board's okay. D0 squared phi. Then, okay, minus D0 becomes minus del squared plus, well, let me write it this way. Minus del squared minus m squared. That's this minus sign, and this is minus that stuff. Okay. Acting on e to the minus I Q1 dot x phi. Now I want to integrate this guy by parts because we're still under well, a full four-dimensional integral at this point. I can integrate the Laplacian by parts, and I'm going to have e to the minus I Q1 dot x times what? There's a D0 squared phi. And then this is going to become, two integrations by parts doesn't change the sign. So we still have minus, but now the del squared is acting on the phi. And then we have plus m squared. And that's the wave operator acting on m squared phi. The wave operator acting on phi. And then I pulled out the RKX. So, oops, hit the cat. So all of this is going to become, I'll just write the P here for that final state. Then we have all these coefficients, minus I over a bunch of 2 omega z, 2 pi to the 3/2. This is a place where it'd be nice to stick in a 2 pi, but we don't. Then d4x where time goes from minus infinity to infinity. And what we've ended up with is that exponential x with the wave operator, the Klein-Gordon wave operator acting on phi. And just call that state Q. And that looks pretty much right. It is. Except for, oh no, that's right. That's basically this difference here. Okay, so let me take a breath while you turn those puzzled looks into questions. How you guys doing? You with me here? Nobody's saying yes. Yeah, that's the way I felt the first time I worked through this stuff.
So I'll ask this.
Yeah.
Or I just would like to check my understanding on, you said it was okay for us to just throw an extra factor of A out in there. And that's because the Pn is just not going, is going to return 0 when we operate on A
That's
out?
correct. That's correct. Yes. All right. An A dagger acting right is the same as an A acting left. So you're looking at this on the out state is you can think of as an annihilation operator acting to the left on the final state. And we've made the assumption that none of these P's equal any of those Q's. Okay. Right? Every particle scatters. Yeah, otherwise you've just got some particle that passes by your Feynman diagram and doesn't do anything with it.
And so, somehow this amounted to our raising operator becoming a wave operator.
That's right. That's right. The place where that difference showed up is in the limits on these integrals. This limit is all the way from minus infinity to plus infinity. The plus infinity, future infinity. So this replacement, a time derivative times a time integral, that allows us to extend that integral over all time. So basically we're doing a full space-time integral here. That's the effect of adding that term. It does not change, well, okay, the thing that changes this into a wave operator is having this time derivative added inside. So once we've done that with turn this into a four-dimensional integral over a derivative, now that derivative acts on the thing that's inside. This is just the double arrow thing. That turns this back into a wave operator, sort of, right? It turns it into a time derivative on phi, second time derivative here, and a second time derivative here can be written as del squared minus m squared, right? Because the plane wave satisfies the wave operator, satisfies the Klein-Gordon equation. Phi doesn't. This is phi. It's not even a very well-defined function of time because, you know, this is a quantum operator evolving along every possible space-time path, if you think in terms of a path integral. So that phi operator, the time derivative of the phi operator, that's the momentum. And that's not a clear function of time either, right? Those are things that we're summing up over every time-like path. At any given time, this is a function of position, but it's not a well-defined function of time. So we can't integrate this one by parts and just get the whole thing to vanish by putting the wave operator on the other side. That wouldn't work. But we can integrate this one by parts, and it gives us the wave operator acting on that, you know, not quite a vacuum solution of the Klein-Gordon equation thing, phi. Right?
So yeah, it's not so the creation and annihilation operators aren't really like functions of time, right? Because they are defined at a given time vector. You like define a TO, and then you create the, but not the okay. So these time derivatives are even just coming from defining the free space annihilation and then noting that the momentum is the time space operator. Is that?
Yeah, well, momentum is the time derivative is what let us write this double arrow in the first place, right? This d0 acting on phi hat is pi. That's where that came from.
Yeah.
Yeah.
As opposed to starting with a derivative in our function for alpha, we started with pi and then defined it. Okay.
Yeah, and I don't know. I don't know whether we could have gone back and if we went back to the original Fourier solution for the wave equation with some Fourier modes and had not done the time integral at that point, I wonder if this might have all looked more natural. I'm not sure. I didn't try it. We're talking about a lot of people trying a lot of heuristics to make sense of this stuff. But it takes some careful thinking about what these objects really are, that the time derivative, it's not a function of time, but the time derivative of it makes some sense as a distribution. Let's see, what else can I say to clarify this? Yeah, this is going to bother us more before it makes us happy. All right, what this operator does, this does annihilate the initial and final fields because those are vacuum solutions. So what's going to happen in a Feynman diagram is that we'll have incoming particles and outgoing particles and interaction stuff. We'll have some kind of pictures with some particles coming in. They'll exchange stuff. Who knows what goes on here, and stuff goes out. And once we get out here, that operator actually annihilates the contribution of these outside legs, which always occur in the overall expression. So in the final expectation value that we end up working with is always going to produce basically the inverse of that for the outgoing legs, for the exterior legs, past and future. We're always going to see that cancellation. So essentially, there are a lot of ways to say this, and none of them makes me just glow inside with happiness. It's tricky stuff, but this does massage this thing ultimately into what we're after, which is by extracting this wave operator that only annihilates this in the initial and final states, we have eliminated one Q from the expression. Now we're going to do it for every Q and every P. So we're going to have a product of M plus N of these things sitting inside. And, who asked for something that complicated? But that's where we're headed. So brace yourselves. This calculation that we're doing here, we're going to do all at once for each incoming and outgoing particle. Let me see. Now, the other thing we have to do, let me see if we're here yet. What we've got is what we intend to get to, this expression. Okay, so we've turned this into that. Now, there are two things we need to do. We're going to do this for each momentum in the initial expression. So this Q doesn't include Q1 anymore. So we're going to have a product of M plus N of these integrals. And The other thing we're going to do is write these phi's. We're going to deal with their time dependence. The annihilating pom-pom. I've got to put the Feynman cheerleader. Ooh, ooh, ooh. Yeah, just watch it or I'll start to sing.
Oh, no, that's the picture. That's the picture you drew. That's all I was saying.
Oh, the picture. Oh, it is, isn't it? Woo! Yeah. Uh-huh.
Yeah, provided a surprising amount of motivation.
Or we're a werewolf, right? You know, that could be a dog with a snout. But the pom-pom's good, that's right. Okay.
Making sure we stay focused is all.
Yeah, all right. So we're going to put the fields in the interaction picture, all right? We're going to deal with the time dependence of this field in an operator sense, right? We're going to put in operators that characterize the time dependence here. And that's next. So hold your hats, folks. Hold your pom-poms, folks. Here we go. Let's see. All right. So one thing we need is, right, if we try to do this for another state. Is everybody good here with the board? All right. We run into a problem of time ordering. So, so we've got our p states here, and suppose I pull out an out state to remove one of these p's, p1 say, and we've already pulled out an in dagger operator with a q1 on our q state. Now, in order to insert this extra operator, so I want to replace this by a out minus a out a in at the initial time t0. This is t final here. So I want to make that replacement for a out, and for a in dagger, I want to subtract an a out dagger on this side, and this is at some q1. The problem is that in order for this in we've added to give 0, it has to act on that initial state. And it would be annihilating, all right, remember this is P1 here. So the annihilation operator we would add here, we want that to act over here on the initial state and give 0 so that we can add it. The problem is, to do that, it has to pass some A daggers, and it doesn't commute. So what we need to do in this product of things we get is we need to insert a time ordering operator, which I'm gonna make some sort of elaborate P to denote, T, some elaborate T to denote the time ordering operator. And it's just what you think. You put the earlier times to the, well, that's your right. Put the earlier times to the right, the later times to the left. So concretely, if you've got two fields, phi1 and phi2, or let me make it phi1 at P1, phi at P2, because these are all Klein-Gordon fields. I can write that as a theta at P1, the time component, minus P2, the time component. So if P1 is greater than this time is after that time, and so we just leave it as phi of P1, phi of P2. And I'm really getting in my own way here. And then we add this the other way around, P2 minus P1, and we write these in the opposite order. So that's a precise way you could write the time ordering operator on a pair, and you can iterate that and figure out what it has to be for some arbitrary finite number of fields. So we're going to insert that operator, and that's what allows us to put in these arbitrary numbers of, well, these doubled creation or annihilation operators. So let's see, why is yeah, those, yeah, okay. All right, that's the reason we need the time ordering operator. And so from here on, we're going to use the time ordering operator. We're going to have the time ordering operator in the expression for this product. And now, okay, boom, we're just going to do all the rest the same way. So let's see if we can write the resulting expression. So I want to write something like this. I just erased the coefficient here, but I want to write something like that for everything in sight. Bye-bye. So let's see. Yeah, that's right. So here's our initial transition amplitude. And we're going to have a factor like this one for all m plus n particles. That's no longer there. Then we're going to have a product I equals 1 through n of, let me see how I've written it here. So integrals d4 yi over all space here, all space-time. Let's see, and then a similar product, j equals 1 to m, integrals d4x. So, okay, so we're up to 4 times the quantity m plus n integrals here, all of which are going to end up giving like either deltas or integrating over deltas. Then for each thing, we had a plane wave, right? So we have the sum over pi dot x dot yi, sorry, pi dot yi, better make that a k. And then, let's see, there's probably a, was it a minus I there? I think it was. Yes. And then we have a similar thing, m equals, no, can't use m, L equals 1 through m. This is running through n. Q sub L dot X sub L. four-dimensional dot products. And then we have a product over I of wave operators and J of wave operators. And then sometimes that times now vacuum states at plus and minus infinity of the time-ordered product of fields. So we have phi of, this would be y1 through phi of xm. So product of n plus m fields here. And again, the vacuum state at early times like this. So look how much we have simplified our transition element. Yes, go ahead, grin at the irony. Yeah, just give you a minute to digest that. The only thing here that I, this coefficient is dependent on the normalization of the green function, right? So we set the Klein-Gordon operator equal to just a Dirac delta. We could have put anything times that Dirac delta, you know, multiples of pi or whatever. The other thing that comes into the normalization here is the normalization of our Fourier integrals. I've always gone for, you know, 1 over square root of 2 pi for the transformation and 1 over square root of 2 pi for the inverse. But what actually helps us remember the powers of 2 pi to use is to put them all in this expression. So we actually want to have a 2 pi, is it a 2 pi squared here? 2 pi to it's, you know, it's actually hard to backtrack and work through these. I'm going to use a different normalization at some point as we start actually evaluating some of these expressions. I'm going to be putting a full 2 pi with each forward Fourier transform. And then we'll stick with that because that's going to be soldered into our Feynman rules for evaluating all this stuff. But take heart, it's just a normalization. We got plenty more to worry about here than a normalization. So let's press on. Now, let's see. What can I say to help? This is confusing stuff, right? It's gonna get easier. You know, these manipulations are just, yeah, really? But yeah, really. There are other ways to get at this. Let's see, I think if you look at, say, Ryder's book, R-Y-D-E-R, Ryder does this with a path integral formulation. You know, I've followed more closely with, which one? Oh, this British one. What's the name? I've lost the name now. But, you know, there are various different quantum books do this in different ways. So the thing that actually gives you confidence in a weird method like this is that a half a dozen different weird methods all give the same results. So you can do this a number of different ways and come up with the same stuff, even though you feel, well, can I really do this step? Well, yeah, in the end it works. So promise, we're okay here. We're actually going to get stuff that's going to predict, you know, 12 significant figures to the fine structure constant. You know, the proof is in the last 50 years of pudding. right? This stuff is very well tested. So, these techniques are still being hammered on. Yeah, maybe. Well, let's just press on. One thing.
Question, Professor?
Oh yeah, sure.
Yeah. Okay, just about this time ordering picture. So, is kind of the idea with this that, like, okay, so we want, like, I guess I'm a little fuzzy, but the idea I'm getting is that we want like our annihilation operators to act zero on to the left, right?
Yeah.
So you're kind of like you're picking earlier times to the right, so that at a later time the operator is like constant, right? It becomes a constant operator. It stops. It has a zero annihilation at later times. So it almost seems like. Yeah, I guess I'm a little confused, obviously, but just you're doing this so that, I mean, is that the picture? Yeah, I'm saying like levels where each one is then turning off at a certain point, but.
Yeah, so what we want to add in something like minus a dagger out here, but that's at a late time, so the time ordering automatically moves it to the left.
Yeah.
So we put it in here so that we can write it in that integral. That's going to give us some field operator evaluated at Q1, but because this is an out thing we've added, that's actually at a very late time. So this operator is going to automatically bypass these intermediate fields and move that a dagger over to the left. Oh, I'm sorry, you can't see what I'm pointing to.
Yeah.
Right. So the time ordering operator puts them where they need to be to give zero.
Yeah.
But we write them where we need them in order to make the limits on this integral run from minus infinity to infinity.
Yeah. Okay. Yeah. I guess that's maybe like there's like sub interactions. We're like kind of like ordering it by like, oh, the first momentum state cares about the interaction for this long, and so we're gonna do it first. Like it almost seems like we're sub-indexing the interaction by like when the final states matter or not. I don't know. Sorry.
Yeah. Well, and we're gonna fully digest this time dependence next, actually. Yeah, you know, that's right. And we're going to be looking at an interaction picture where the time evolution of fields gets sort of more or less separated from the interaction. So the interaction is only going to happen sort of on the way from here to there, right? And we're going to be doing lots more with time ordering. What we really want is not time ordering, but normal ordering. Normal ordering would make things zero, right? It'd push all the annihilation operators onto that vacuum state and give zero. So we're going to prove Wick's theorem. We're not quite there yet. Won't get there today, but we're going to prove Wick's theorem, which relates an arbitrary ordering of fields to the normal ordering, you know, plus a bunch of commutators. And by the time you apply that to all of these fields, you get a sum of products of commutators, you know, so the theorem itself is like massive. But anything that retains even a normal ordering of some subset of the fields is going to have the annihilation operators acting on the vacuum state and give zero. So the only thing that survives is a product of all these commutators. Well, each of those commutators turns out to be a green function called a Dirac propagator, which we will write in momentum space. And those are the propagators that we put in, one for each line in our Feynman diagram. So, you know, we're gonna see, you know, a little bit more familiar picture emerge here, before too long, but there's time dependence, interaction picture. Let's define the interacting fields. I hate to erase this, so I'll leave it up here for a while and work over here if you can see this side of the board. So I want to define the interaction picture field as more or less the opposite time dependence from the usual. If we take the field and we sandwich e to the I Hamiltonian times say t minus t naught on the field at x and t naught, and I'm already violating my boundaries here, times e to the minus I Hamiltonian t minus t naught. Let me check my signs and things here. Yeah, we're good. So we can evolve our fields using one more point. This is h naught. So the normal evolution of a field would be e to the minus I ht on the field e to the I ht, something like that with the full Hamiltonian here. And probably the opposite signs if we wanted the usual Schrodinger picture. But the interaction picture field is defined this way. Now, what this more or less does is it leaves the time evolution as being only due to the interaction part of the Hamiltonian. We're picturing the Hamiltonian as being written as a free particle Hamiltonian plus an interaction Hamiltonian. We've seen an example of an interaction Hamiltonian when we gauged the Dirac equation and got that term where we had a psi bar a slash psi as the current source for the the variation of this with A gives the another current as a source for the Faraday tensor, and varying psi here, we get the vector potential feeding in as part of the covariant derivative in the Dirac equation. So it couples the equations. Well, the thing to notice here is this is a product of fields. And the ultimate evolution we're going to get is the exponential of the interaction Hamiltonian, which we expand in a power series. So what's happening is that the time dependence will be free field evolution, which we can handle very easily, and then a final exponential in the interacting Hamiltonian, which ends up being a product of fields. So we're always going to be evaluating this matrix element where these are all interaction picture states, and there's going to be a single interaction Hamiltonian expanded in powers. So we're always looking at vacuum expectation values of products of fields. And you can generate that with a path integral. You can do it the way we have, more or less canonical quantization, but the Feynman rules let us write down such things very directly. So still, what we want to do is write all of the fields in terms of these interaction potentials. And the thing about this is, okay, the time evolution of this field is governed by the free Hamiltonian, which means that these interaction fields are in fact evolving as free fields, right? the you know, the Fourier expansions we've written for fields are valid for these guys. And then the time dependence, let's see, now, how do we do that? The full time dependence is given by the full Hamiltonian. So now, let's see, what is it I want to write here? Yeah, let me write the full field. Okay, so the full field at x and t is e to the I full Hamiltonian t minus t naught times the field at t naught e to the minus I t naught like this. And now I want to insert identities. This and its conjugate. So I want to write e to the I Hamiltonian. You know, let me just take t0 equals 0 so I don't have to write quite so many things here. So IHT, then we have e to the minus I free Hamiltonian t e to the I Hamiltonian free Hamiltonian t phi. And then identities on the other side, minus I free Hamiltonian t e to the I Hamiltonian free Hamiltonian t e to the minus I full Hamiltonian t. And now these inner three become the interaction field. Times now this becomes phi I. Oops, plus. Now, we can't quite combine these because things don't commute, but this product of fields actually satisfies a fairly simple differential equation, so we can get at its properties. This is this guy is, I'm going to define it to be u of t minus t naught, I think, yeah. Yeah, u of t and t naught as the unitary operator that takes us from time t naught to time t. So with that definition, I guess I really do need to get rid of our expression here. But we'll see it again. It's going to prop up in exercises. But not yet. So what this says is that phi of x and t, and we're going to write as this time translation operator, dagger, on the interaction picture, u of t, t naught, like that. So now we need to find out a bit about this time evolution operator. If we take a time derivative, ddt of, yeah, so suddenly this is all going to feel sort of normalization. U minus h t minus t naught. So if I take a time derivative of this thing, I can pull that, I'm going to pull down a minus I h. But this is the same operator here. So I can write that h on either side. I can put the h over here if I want. So I'm going to put it on whichever side is convenient. What that means is if I take the time derivative of u of t and t naught, now I'm going to get right? U is this thing down here, it's this product. So I'm going to get one term where H naught comes down. I'm going to have e to the, let's see, I have to think where I want it though. Let me remind myself, yeah. So e to the I H naught t. I'm going to bring down the stuff in the middle. So the first derivative brings down an H naught, and I put that in the middle. The second one's going to bring down a minus H, and I'm going to put that in the middle. So now we get the difference between these two, sandwiched between them. T minus T naught here, minus T naught there. And all right, that difference is the interaction Hamiltonian. And let's see, we just have to, hang on. Yeah, it's a sandwich of the time evolution Hamiltonian. So minus I e to the I H naught delta t times the interaction Hamiltonian times e to the minus I H delta t. Sorry to just write delta t there, but you guys will know what I mean. Now, what do we do with that? I want to turn this back into an operator acting on U. Oh yeah, I remember. Okay, so I'm going to stick in another identity. So we've got the interaction Hamiltonian here. Then I'm going to put it e to the minus I H naught delta t times e to the I H naught delta t times this, but that's U again, right? U is that product. So half the identity goes into giving me another U here. And now I'm going to define this thing to be my interaction picture Hamiltonian. So the original interaction Hamiltonian with the time evolution appropriate to the free Hamiltonian is what we call the interaction picture Hamiltonian. Just like the interaction picture state, it's that same sandwich. So now U satisfies a nice differential equation, ddt of U of t naught is minus I times our interaction picture Hamiltonian times U of t naught. And that we showed in quantum mechanics has can be written as a time-ordered integral, right? So this implies that U can be written as the time-ordered exponential of minus I times the integral of the Hamiltonian over time, dt from t naught to t. That's the full expression in the most horrible of circumstances, right? We talked that through in the quantum mechanics class. Oh boy, that was fun. But normally in quantum mechanics, H doesn't even depend on time, so you just end up with minus I H times the time difference. And that's what we're going to end up writing much of the time. We won't really have a time dependence to worry about in this. And so we'll be able to write this just as a simple e to the minus IHT. Okay, how you guys doing? You got any questions at this point? Let's see. Yeah, these U's also have a product rule, and we're going to use this to simplify our expression. You know, we I've erased it now, but the expectation value we're after here is a vacuum expectation value of a product of a whole bunch of fields. We're going to turn all of those fields into the interaction picture, and all of the and the whole thing's time ordered. So what we can do is look at a product of a whole bunch of U's, and we can smack them all together into a single big U, multiplying a product of interaction picture fields. So let's finish up with a quick proof of this product rule. Let's see, how do we want to prove this? Yeah, so suppose we have a derivative of a product of two U's.
I'm sorry, I may have a stupid question. Sorry.
You know, no question at this point is a stupid question.
Oh.
Come on, this is messy stuff, believe me. Yeah, but what's your question, Alex?
Okay, so I'm just looking at like 913. So is the reason, like, so when we have the time ordering operator on this like integral, is that just to say that if I tried to break that integral up as like the sum of the integral from t0 to t1 and then t1 to t0, that I would time order, because then you'd get products of the two integrals, and then when we expand
right.
E out, we time order. That's what that means. Right.
Yeah,
okay.
Yeah. I did like a second order example of this, I think. Yeah, let me remind you of that if you're not recalling what we did in quantum.
It just seems like this is a really nifty way to like solve any type of like time operator differential equation, and so I'm just wondering why.
Yeah, it's a handy trick, but
yeah.
So what you do, you know, in your expansion of now, let me think. We're taking a product of a bunch of infinitesimal HDTs, right? So when we're trying to get from the infinitesimal expansion to the full thing, you know, we've got a bunch of things like this. And if you just look at two of these, okay, so the first two are fine. Those are going to add together. So you're going from, say, T1 to T2 here and T0 to T1 there, right? And this is acting on your initial state. So you take it one time step, now you take it another epsilon time step. And the problem comes when you get to the second level. So at the first iteration, you're going to get, you know, the integrals just add and you get T0 to T2 HDT, no problem here. But now at second order, you have an epsilon squared, and now you have the product of these two. And that's fine, they're different times, and maybe these are later times, but that's not gonna let you write it as an exponential. So to write it as an exponential, you look in the T1, T2 plane, if this is T1 and this is T1 and T2, say, right? You look in that plane and you realize that what you're integrating is over all, you're integrating over all T1 that are less than T2. Did I draw that right? So yeah, you can integrate in T1 as long as it doesn't exceed T2, right? And that's fine. But what you do is say, well, you know, that's the same as if I integrated the other way, only the time ordering is backwards. So you look carefully at this and realize, oh, I can integrate both integrals over the full range if I time order and multiply by a half. And then I can write it as the series for an exponential by doing both time ordering and putting in the factorials I get just the expression for an exponential. The bottom line, it always means this infinite sum, right? It's always actually something like this. So, you know, when in doubt, go back to the Taylor series for the thing. And that's, there's a helicopter flying by.
So time ordering is kind of always happening on the level of functions on operators. It's like an operator of operators on operators.
Operator products. Anytime you've got a product of time-dependent operators, it's probably going to be handy to use a time ordering operator. I mean, you know, and you know, the thing that makes this picture simpler is these integrals here are all over different ranges. Whereas here, each integral is carried all the way from your initial time to your later time. And, you know, if you can write things that way, it helps. Yeah, I don't know if I showed you guys this kind of diagram before, but yeah, so, you know, let's see. Yeah, in the initial integrals here, I forget which I'm calling T1 and T2, but you're integrating over just one of these triangles where the integration range of one stops when you get up as big as the other, because now you would be in the wrong time ordering and you can't commute the things. So by putting time ordering in, you can extend the integrals all the way, and then you just get the same integral squared, but you've done it twice. And one of the times it was out of time order, so you really had to flip them the other direction. Yeah, this believe it or not, this feels better than all those manipulations on the funny double arrow time derivative, extend your integrals and stick in A's and A daggers.
This almost feels like a density measure thing, like you're just sticking on some type of operator density measure somewhere where, you know, the time disordered ones are zeroed out.
No, you're actually doing them all multiple times. So yeah, you're not zeroing them out. You're dividing by the number of times you did the same thing twice. Right.
Yeah, sorry, that's what density measure. Sorry.
Yeah. So this turns into a 1 over k factorial at kth order. And
yeah, what I meant. Yeah,
I'm not
right.
going to try to draw that picture.
As opposed to zeroing out the time disordered ones, you can just figure out its relative density in the total ordering.
Yeah. Okay.
And then ratio it out.
That would be right. That's right.
Dang.
Yeah. Yeah. Good. So okay. So I didn't quite get to the product, but the product of u of t to t1 with u of t1 to t2 is u of t0 to t2. But that's a short proof. I'll do that next time. And then we go back to the matrix element and put in this time dependence and try to simplify that. So picking up here next time. Yeah, take a deep breath, maybe read it over again. It's, you know, you murk your way along feeling, well, this may not be wrong. This may not be wrong. And, you know, it's not. It's okay. You know, real smart people thought long and hard about this stuff. And, you know, this is one of the ways they came up with doing it. But yeah, there's a lot of detail to convincing yourself that you're really allowed to do this sequence of manipulations. It will get, you know, like all those box plus m squareds we're going to write as a k squared plus m or a q squared plus m squared, and we're going to see they'll cancel every time. that always exactly cancels out the incoming and outgoing legs. And yeah, we get 5 minutes. It'll be swell. I can stick around for questions. We ran out of time here, but yeah, I know what it feels like to work through this because I just wrote this stuff and oh my, trying to say clearly, what it is you're doing at any given step. Yeah, well, I made a stab at it.
I had a question, I guess, on this general. If we put like boundary conditions. Oh, okay. Bye, everyone. So I'm just at that string theory conference. Obviously, they were talking about. I guess that's what I'm just gonna fish here for is try to. So they're doing stuff like working in ADS space and stuff, and then like doing cuts on the ADS space and gluing ADS space solution. Is that like they're changing the Green's free solution here? Are they basically just like, we're gonna solve for the free space solutions in this partial, this different geometric space, and then glue the, I guess I'm just wondering, yeah, what level the space geometry interacts here.
You're allowed to paste geometries together as long as, it's like any differential equation. You're solving, say, the Einstein equation. You want to paste one space to another to make, say, what's the worm, that first wormhole called?
The Einstein.
Yeah, the Einstein-Rosen bridge. There you go.
Yeah.
Well, you can't cut just anywhere. You've got to match the metric and the rate of change of the metric. The zeroth and first derivatives, right, have to match. That's true at the horizon. The derivatives match too, so you can piece them together there. If you're in flat space, you can put 2 slices in flat space, attach this lower lip to that upper one and that upper one to that lower one. The metric is 0 at perfectly allowed space-time. Closed time like curves, cool. That's the solution to general relativity because the curvature is 0. So you can do weird stuff like that and produce either very funky spaces or some ones that are doing just what you need. But you need to just match a couple of boundary conditions probably.
So in each of those cut subspaces though, like I guess what I'm asking is like, when you're gluing those 2 spaces together and you develop like a Green's function for some for some differential equation there, is your Green's function solving? So I guess what I'm wondering is, are they trying to figure out how the 2 individual Green's functions meet to form a total Green's function? Or are they like maybe starting with a total, like, do you see what I'm saying? Is I'm wondering like, what does the cut, is the cut a boundary? Like, are they matching 2 fields and then saying they match at this inner boundary? And then they also meet an outside, closed space boundary totally, or I don't know the exact problem you're talking about, but you could do that. I mean, the Green function is a solution to a differential equation, and if you match at the boundary conditions, gosh, let's see, so you have certain boundary conditions on a Green function. Just whatever space you're in, it has to.
Yeah. Well, it vanishes everywhere but a point, and if you're doing Dirichlet boundary conditions, you want it to vanish on the boundary.
Yeah, whatever you're.
Yeah. So, as long as so if you've got 2 spaces.
With two Green's functions known, I guess.
Found the Green function for each one. Yeah, I think if you think of it as just a differential equation, you have to match boundary conditions at that boundary. Well, probably both green functions vanish there. They vanish most places. So it may not be hard to match those boundary conditions.
So yeah, the talk that I guess that I'm kind of picturing too, I can't remember. It was one of the postdocs from UT Austin, but so they were trying to do they were doing string theory, and kind of I know they were in two ADS spaces, so they wrote down like the Poincare bubble was the picture they were drawing, like the circle, the Poincare circle. But what they had in it is they were one half. They had some type of like conjunction angle where they would make, you know, half of the Poincare is complete, and then the other one would have a sliver, a crescent with an angle at the hyperbolic center. It was deviant from pi. And so what they were doing is they were deforming half of the space and gluing them to each other, and they had a black hole string in the exact center of the space. So the picture was like black string down the center, and then a cut space that was getting glued. And what they were measuring was like, so I think what they were trying to measure is like how long it would take for the entire space inside, because of the Hawking radiation, to become entangled. They had some time calculation. It was like a Robin time or something, some time that they were, yeah, but okay. So sorry, that's, I guess, that's kind of the setup that I'm just wondering, like, is the geometry like affecting the free space solutions? Like, what were they perturbing when they changed the geometry there? Like, that I could grasp, like yeah.
Yeah, it's not obvious.
No.
Let's see.
I didn't understand a lot, so my explanation is incomplete.
Yeah, you know, I mean, that happens a lot at conferences, that, you know, people, you know, have to abbreviate the research project so much that it becomes really hard to know what they're talking about a lot of the time. But yeah, it's more a matter of, oh, that's interesting, such a thing exists and somebody's figured it out.
Right.
Yeah. But yeah, no, I don't know what they're doing. You know, that's not like a construction I've seen before anyway. But you can paste spaces together. You have to match some boundary conditions. Uh-oh, I lost you. Can't hear.
My computer's about to die. I'm sorry.
Oh, okay. Yeah, I couldn't hear what you were saying there.
You can paste solutions together.